All right, welcome to the fourth session. It's my great pleasure to introduce Casey Ting, who will talk about intelligence-empowered vertical farming systems. Casey, it's...
Good afternoon. Well, I hope everybody is awake. All right. Well, this is a time that actually a lot of our international webcast participants started to go to sleep. I know my co-author, my co-presenter did that. Anyway, I want to recognize my co-presenter, Dr. Wei Fan. He is professor and chair of a department at the... What? I didn't do anything. Oh, good. See, still engineers. So he's from Taiwan, and I invited him to be a co-presenter. You'll know the reason why. I've been enjoying a lot throughout these presentations, but after 12 speeches, I was wondering, what is there more to talk? So the challenge is what to say. Okay, but I have been accused for being too philosophical most of the time. Therefore, that's why I brought Dr. Fan in, because he is very practical, and you'll see many of his slides embedded in my slides. That's true collaboration. I didn't just show mine and his. I actually show both together. Okay, so I'll quickly go through. The time is limited, so I'll quickly go through some of the things. I'm emphasizing automation and systems analysis today. That's how we bring intelligence to enable machines to do what human can do. Also enable human to solve problems in a more systematic way. So as a system engineer, I need a model. So the first thing I will show is an ACE-SYS model to describe what a vertical farming is. And then I'll go into intelligence-empowered vertical farming systems, some challenges in automation and systems analysis. And then I will introduce a term called concurrent science, engineering, and technology, called consent, which is something we have been building for another purpose. Okay, I've heard the name concurrent engineering. That was very good. So and I will show you some more slides about vertical farming in operation in Taiwan, and 3-4 slides, and then some key technologies as viewed by Dr. Fan, and I agree with him, and also some opportunities in those areas. Okay, the ACE-SYS model came about with Dr. Giacomelli, I don't know how long ago. We don't want to reveal our age, but so we figure it's a very complex system. That word was used this morning. Then how do we handle it? How do we come up with a systems approach to be able to address and handle and approach and solve the problem? So basically, there are 3 technological parts: automation, culture, and environment. And then integrating all these 3 into a system. And you're all very familiar with that. So I'm embedding Dr. Fan's slides from time to time. Now you'll see some real commercial vertical farming system, or he calls it plant factory. I think he was inspired very much by Dr. Kozai's work. That's why the term plant factory. Now, what is ACE-SYS concept? So you have automation, which is very important. How do we add intelligence to mechanized system? That's automation. And then cultural part is biology of plants. Okay, how they respond to environmental factors or manipulation, physical, mechanical, chemical, biological. Environment factors, we have seen that a lot. We need to be able to control the environment. And sitting in the middle is systems. Okay, each individual technology would not work for vertical farming. We have to integrate them into the 3 circles together. But we are not naive. We know on top of that, we need to have a scaled, sustainable business model by considering other factors. Because people may want to go into this business to solve different kind of problems. So social, political, economic, policy, and all those. And at the bottom, workforce development. How do we produce human capitals who will have this kind of skills and knowledge to be able to operate in this domain is very important. So how do we empower vertical farming system using intelligence? This has been said before, even better than I can do, but there are 3 parts. One is intelligence. Intelligence is not all about technology. Intelligence is all about how to use the right information at the right time to solve the right problem. So we start with information need instead of looking at technologies. Second thing is mechatronics. Then technologies come in. We need to know how to use the information, and we need to know how to execute our tasks. So manipulators and effectors and even control systems are very important. System integration, again, do we go into fixed or flexible automation? There was a question about why the robotics for vertical farming, they operate so slowly, because we want it to be flexible. If it's a fixed automation, it can be very fast, like printing newspapers, okay, doing the same thing, high volume, over and over at the same time. But because of unstructured environment, that makes the slowdown of these kind of things. Now, automation, repeating what's already said before, perception, very important. Understanding the environment, using all the sensors, sensing technology, try to understand what's going on around you. Reasoning and learning. After you understand it, you need to be able to process the information to make decisions. Okay, that's where heuristic, mathematical, logical, all kind of reasoning methods, learning how to make machines learn so it can accumulate knowledge through experiences, just like human beings. These are all human capabilities we try to add on to the machines. That's why it's intelligent. That's why it's called automation. Automation is to add all this onto a mechanized system. That's automation. Communication from machines to machines. They have to know what's going on. They have to be able to communicate to each other. Image processing systems should tell robotics hand how to do things. Task planning and execution. If we just do the first three, that's just good to know, good to have, but we need to get work done. So we need to plan the task. That includes control, algorithms for environmental control, too hot, too cold, not enough light. Also execute the tasks like Dr. Kondo's good work or manipulating all kinds of objects, subjects. System integration again. Okay, so you know I like the word systems. You know, so my former dean told me every other word I speak is systems. So I hope it means a good thing. Anyway, so there are challenges how we automate. We have to make return on investment very attractive. It's been said. System optimization. We have been looking at many, many workable systems, but I'm wondering how many of them actually have been optimized. I think the key of intelligence and system approach in automation is to be able to optimize, not just to come up with a workable system. We have to build our capability to find the best ones among all the good ones. So that's optimization. That's very important. Okay, we need to also understand whether we should do fixed automation or flexible automation, because there's a different ways of using those things. Multiple use of machines. Can we create multiple use of machines and parts so we don't have to do one of a kind and then let it work for 2 days and sit there for 363 days, right? That's correct. So the math, when you stand here, math is a challenge. Anyway, so multiple use, limited market demand and acceptance. I was talking to someone today. I say, a lot of times I feel, it's not a criticism at all, it's observation. In this field, control environment plant production, however we describe it, we are waiting for other areas to bring technology to us so we integrate them. We need to lead in the technology development by knowing what we need to do specifically for our field, and then we spin off to other disciplines. We cannot just wait. Okay, so we need to know how to generate market demand and acceptance, not just buy from other disciplines and use them. We need to actually be the lead of technology development and then spin off to space use, to defense use. Concern for safety, that's very important, right? We know that. And then we need to build our capability, not coming from a university point of view, the continuous improvement of research and development capabilities. We really need that. Without that kind of investment, we cannot go very far. Okay, and challenge in systems analysis. I started calling it a systems informatics analysis, because we need information, we need analysis, and we need to make decisions. So there are three parts: information, needs, and processing, and how to make decisions based on that. So there are some challenges. Do we analyze a case by case, or do we come up with a tool that can help you analyze many cases? Okay, that's very important. Also, the tools we develop in analyzing certain situations, is that transferable to other situations? System abstraction is always the most difficult thing, because how do you tell a story of a system? If we cannot come together and tell the story of what vertical farming is, we cannot solve the problem. We know that. We tell our students that, then we don't practice that. That's not very good, right? The first thing is to be able to divide, describe, tell the story. That's the art of system abstraction. That's very difficult to teach, because you abstract the system for different purposes, okay? And we have seen that in politics. So targeted participants and audiences. Who are we making decision support for? Okay, so in the end, we are providing decision support. We may not be making decisions, but we are helping others make decisions. So we need to know who needs what information. Validation. How do we know the information? This is the information trust issue. How much do we trust the information? Handling all these uncertainties, heuristic and complete information. What do we consider as deliverables? Okay, we have to deliver something. We have been blamed as a modeler or system analyst. We always try to improve our model, and our job is never done. So it's a job security thing. But my response is that we are not trying to perfecting model. We are trying to make model useful. Once it's useful, let's use it and do something. Okay. So, and coordination of activities. I already mentioned this word consent, which is the platform we're building. So specifically, just to give a very top level of idea of what we mean by consent. So you look at physical space at the top. That's where we build. That's where we see. That's where we see all these 20 stories of vertical farm, right? But then we need to analyze it. The best way to analyze it is not in the physical space. You cannot build it and test it and it fail and try it again. Very costly. Let's do the system abstraction and inference. Do the analysis in information space. And then, if we stop there, we are not getting our job done. We need to go back and make decisions and implement it into the physical space. So it goes on and on. But beyond that, more than that, we need to consider at least 4 parts. The first part is system requirements. What do we need this system to do? Because everybody has a different expectation of the system you're building. Okay, let's define that. The next thing is look for candidate technologies. We have seen a lot today. What can be used to solve the problem, to satisfy the requirements? Another thing is mission scenarios. We know that if it's on the moon or in the South Pole or in Maryland or in Illinois or somewhere else, they're all different, right? So we need to consider site-specific issues. So in the end, our product is system configuration and design. That's what we are trying to target. So this is the process of, but wouldn't it be wonderful if this whole platform is already in the cyberspace, in the cloud somewhere, ready for us to use with all the information, all the models we need, and all the decision support, translational tool that we have, targeting the audiences and getting a right protocol for scientists to come in and participate all the time, input and output. So that's the platform we have been building for biomass production for energy. Not for vertical farming yet. So quickly, at NTU, National Taiwan University, the university has invested some money to build a plant factory research. This is really vertical. This is on a rooftop because they don't have space. So not that they wanted to put on a rooftop. It's just because of space limitation. They built it there, 320 meters square. This is the inside, how it looks like. It's interesting. Dr. Fan, he came from Rutgers, and he didn't like the word ACES. Oh, no, he went to sleep already, so I can say that. He created his own word, ACE square S. So what he added is energy. So that's another extra E there, but my view is energy is embedded in all these other ACEs anyway. So that's okay. You know, we agree to be different. So there are more commercial farmers. So why in Taiwan this kind of area, plant factory, is happening so fast within the last 3 years? Because all these stars are lined up. Okay, you have universities supporting it, governments promoting it. I met the Ministry of Agriculture in Taiwan just several weeks ago. He really promotes it from the ministry. And real estate developers, builders, construction companies, HVAC industry, all the important key players are lined up getting into this game. Okay, I will show you another 3 or 4 of this. This Everlight company is an LED company. You know, Taiwan makes a lot of LEDs. So they are into this kind of business. They invest into the beginning is that they wanted a system like this to provide leafy vegetables for their employees, okay, as a benefit, okay. And then they start to grow. This is Pacific Group. Pacific Group they build high-rise condominiums. I saw that from, they actually provided, see, when you buy a house or a condominium, they give you refrigerators, washers, dryers. Instead, they offer them a unit like this, very smart, so you can sell the house, sell the condominium, and you sell the small plant factory to go with it, okay? And they actually built another facility next to a supermarket. They even have the educational facility to go with it and tasting facility. This is CalComp. I believe it's calculation and computers or something. Must be coming from a control company. So they invest heavily in this with all these different things. It's not my company. Okay, happened to be Ting Mao, but it's not mine. That Ting is not even my Ting. So this company's got Ting Mao. So I visited. You didn't get the joke, right? That's okay. So this is Dr. Fan. Okay, he is the guru of this area in Taiwan nowadays. So I happened to visit them 3 weeks ago, and this is the owner. And you see Dr. Godo there from Chiba University visiting. So they have a restaurant right outside of what they produce, and then they serve all kinds of very interesting. There's one plant. They say $3,000 per kilogram something. Have you ever heard of it? It's called ice plant. I've not heard of it. I actually took 2 bites of that. It's many dollars per bite. So actually, okay, I'm getting to the end because of time. Okay, so this is a Philips Wei-Fan's chart. ACEs again, very interesting. So I put ACEs in the middle. Hopefully he's not offended. So this is very interesting. Automation. He said key technologies in Taiwan for vertical farming would be all those automated subsystems to the upper left. And then you need to have high-value crops. That's where selling is the most important. Marketing of the product is most important to keep this going. Environmental control, very important. And then there's a lot of system performance issues. You really have to pay attention, to do that. So this is the integration. So he continues to develop based on this philosophy to advance. Okay, a couple more slides. Opportunities. I was told to present several problems. But I want to give you opportunities, not just problems. Let's improve technology readiness level and economic viability of how to automate information gathering, processing, and materials handling altogether. Okay, we need to improve TRLs for NASA purposes. Build on past success of agricultural mechanizations and also modeling capabilities. It's very advanced. Let's use them. Okay, utilize communication systems and computational perform, like internet. Why don't we use them? The cloud, all these technologies, we have to use them. Enhance market acceptance. Okay, marketing should come in. Potential spin-off technology, I already mentioned that. Okay, don't just box ourselves in. There are other opportunities beyond what we do. But to be able to do that, we have to think bigger, not just say, let's solve this problem today and be done with it. Let's think, how can we solve it at the same time, selling technology to other sectors. Okay, we have to facilitate implementation of emerging technologies. Whatever we do, ideally it should be designed as a plug and play type of module. Okay, so technology change, you don't have to redo the whole thing. You plug something in and then try it out. Okay, the flexibility. For systems analysis, let's establish information protocols. There's a lot of papers, but sometimes papers are good, but you have to read it, understand it, and how to use it. Okay, but it wouldn't be better if we set up a protocols for all the researchers. Concurrent science is for that purpose. Let's get scientists together in a concurrent way. Come up with some way, let scientists participate in a way that we can analyze it, not just give us a paper to read. Ask them to provide information in certain ways. Okay, and we have to have a computerized environment to be able to do that kind of collection of information. Models, we need robust models, so that will make information valuable. We create value-added information using models. Some platform needs to be created for providing decision support. So in the end, I say, let's get together and create a consent platform for vertical farming. Okay, I think that's doable. One person cannot do it. It has to take the whole community, and also it's a huge challenge, but I think it can be done. If a PowerPoint or PDF, if a PowerPoint can be provided for all the people, even myself, to make slides, I think we can create a consent for all the scientists, all the practitioners, all the growers to come in and help each other. Okay, that's my proposal for the day. Thank you very much. Yeah.
Are there any questions to the speaker?
Aren't there existing collaboration engines sort of off the shelf that are already out there?
There are, but I don't know how good they are. I have been approached many times. There are project management, there's a science communication, but they are not consent. They only collect information and tell you where to find information mostly. They don't they don't provide decision support for you. There's a link missing. Okay. It's mostly a search engine for database collection, search engine for finding, but it doesn't really process the information in the way that we can decide when to turn on the light, when to use what color LED for what kind of crop. It doesn't do that.
So even the simulation engine, collaborative simulator.
The simulation, we can build modeling. We don't have to code our models anymore. We can use those games or some Simulink to do modeling. But still, to integrate into a consent, there's some work to be done. Okay. The key for precision farming is exactly the same challenge. Technology is way ahead of decision science. So even machinery companies, they are very interested in not just selling the steels anymore as tractor. They want to sell intelligence that comes with the steel. So they're looking at cloud, supercomputing center providing service. So farmers can dial up to get information to decide on, now I know all this. What do I do with it? That's where the missing piece is. Who can do that will be way ahead of the game, in my opinion, anyway.
We have time for another question.
Oh.
If not, we just
Thank you.
introduce the next speaker, Devin.
Thank you very much.